To the course Bayesian and Causal Bayesian Networks. This is Chapter 1, the Bayesian Network Representation. I want to start the introduction to Bayesian networks with a motivating example. Imagine that you're given a task. You're asked to determine the likelihood, the probability, that a person becomes infected with COVID-19, given that that person does not wear a mask but keeps the social distance. How should we approach this problem? Well, if you're a person with a math background, you may say, let's just go with a mechanistic modeling approach and use differential equations. Well, differential equations are indeed great, but as with any other model, they come with some drawbacks. They require the exact underlying deterministic or stochastic dynamics, based on what you want to choose, that govern the interacting variables. For example, in this case, we need to know the exact relationship between how wearing a mask can affect the likelihood that a person gets infected. What is the mechanism? Now, this can be problematic if some of the dynamics are unknown. Especially, for example, in the beginning of a disease spread, many of these aspects are unknown. Now, also, if ideally you know all of these aspects good enough to use differential equations, if you want to incorporate many variables, then you may end up with a complicated system of differential equations, which the analysis of which can be quite complicated. For example, imagine that we want to incorporate temperature, season, like is it in summer or is it in winter? Does it affect this infection to COVID? What if we know that that person already has fever? How does that change the probability? And many of so on factors. So again, differential equations indeed can be successful. They have proven to be successful in many applications, and they can bring insightful information about the underlying dynamics, but they have these shortcomings. Now, another paradigm of modeling is data-based. Try to use data to answer this probabilistic inquiry. If we try to write down this question by using probabilistic frameworks, we can say that, well, the question we're asked is the P as standing for probability of a variable called COVID, which we will later denote it simply by C. And this variable is binary, either true or false, indicating that that person is infected or not infected. And then we have this given condition on the fact that the variable mask, representing wearing a mask, which is again binary, false or true, and given that that person is following a social distancing, true. So we want to calculate this probability. And then the question is, can this be answered from data? Okay, you may ask, what type of data are you talking about? So for simplicity, just imagine that we have collected a data set from 12 individuals. What have we collected? So here we have 1, 2, 3 to 12, each row representing an individual. Individual 1, we know that was infected with COVID, because it's true, but didn't wear a mask, did not used to wear a mask, which is false, but abided by social distancing. And so on. Like the second person was not infected, but did wear a mask and was abiding by social distancing, and all the way to the 12th one. So how can we use this table to answer this inquiry? So see here, I have absolutely, or at least I'm not using any information of what is the relationship between mask and COVID or social distancing and COVID. I'm just blindly looking, ignoring all of that part and just only looking at this table and want to answer this. Okay, so how to do this? Let's start simple. Imagine just that we don't have this social distancing part, and we want to determine the probability of the person being infected, given that that person is not wearing a mask. So how to answer this? Well, let's use conditional probability, by definition, this P of C given M can be written as the joint probability of COVID and mask, C and M, divided by this second part, conditional part, which is mask. So now how to calculate this, COVID and mask? Well, by just looking at the table, I only need to see how many times the variable COVID is equal to true and the mask is equal to F, false. So COVID, mask, how many times the first one is true and the second false? 1, 2, and here I have 3. So 3 in total, true, false. So out of the 12, 3 of them happen to be what I'm looking for. So the total probability will be 3 over 12. Okay? So that's with the numerator. What about the denominator? For that one, probability of mask, I will use the marginal probability formula. So it's just that P of mask being equal to false means that I don't care about COVID. COVID could be false or true. I just want to know, I just want to have the second one being false. So here I will just look in this column which ones are false. So I see like 1, true, 2, 3, and 4. And you see some of them here it's false, some of them are true. I don't care. I just sum them and then I will get 4 falses. So this will be 4 over the total, which is 12. And now I can put this 3 over 12 in the numerator, 4 over 12 in the denominator, and I will get the total of 0.75. So based on this data set, I can say, and of course under some practical assumptions, I can say that the probability of being infected with COVID if you don't wear a mask is 75%. Now, what about the original inquiry? The probability of COVID being false given that I wear a mask and I abide by social distancing. Here it's a bit changed. Both of them are true. So if I want to answer this, I will use the same technique. I will say that this conditional probability can be written as in this form, and then if I use the full data set, to answer the denominator, I just need to count how many times in these 12 individuals COVID was false, mask wearing was true, and social distancing was true. Okay? And here you see 1, 2, 3, 4, 5. They're indicated by red. So it will be 5 out of 12. And for answering the second part, I will use marginal probability. It means that I have to marginalize out C. I don't care about it. I just look how many times M was true, D was true as well. So I'm counting these ones, and then I will end up to 6. And then again, I will put it here. So the total probability will be 5 over 6. Okay? Now I answered this question, but what about other types of inquiries? Like the person being infected with COVID and not infected with COVID and wearing a mask if we know that that person was abiding by social distancing, or other types. Can I come up with a pattern here? Can I find a systematic way to answer these questions? And the key is, the key appears to be the joint probability distribution. If I know P of CMD, this joint distribution, then I can answer any inquiry. Because as you see, first I can just turn that conditional probability into a fraction of 2 non-conditional probabilities, and the one that appears in the denominator, I can use a marginal probability to calculate that. And both of them are based on this whole joint complete probability. So I just need to calculate this. If I know this, then I'm done. In this case, with 3 variables, so all are binary, I will end up with 8 possibilities. So COVID 2M has 2 cases, and times social distancing 2 and then I will end up with 8 possibilities. If I want to visualize it, I can say, well, I have CMD, I have 8 possibilities. This is not a data set. That's why we use a different color here. It's just the whole number of possibilities, and for each of them I need to calculate this probability based on the data set. So for example, what is the probability of C being false, M being false, D being false? And I can go back to the table and see that, for example, if the case where all of them are false, I think it's only this one here. Okay, and so it's 1/12. And here you go. Some of them will not even appear in the data set. False, false, true. So that's why we put 0 here. 0 divided by 12, which is just 0, and so on. So I can calculate all of them. Just note that the number of parameters we need is this P1 to P8, but because they're probabilities, they should add up to 1. So I indeed need 7 parameters, not 8. Okay? Okay, so to conclude, here I try to reveal the key role of joint distribution. If we have the joint distribution of the variables of interest, then we can calculate any probability in query using this conditional distribution and marginal distribution. Okay? And so we can just look into these joint distributions to find them. So I want to say it right here that kind of the whole goal of Bayesian networks is to help finding these joint distributions. Okay? And we will see why this can be challenging. Okay, so before that, just a few recalls. If you don't remember exactly, given some random variables x1 to xn, the joint probability distribution is the probability of having all of them together, p of x1, x2 to xn, with the different possibilities, like x1 can take different variables, values, x2 and xn, and so on. Marginal probability distribution is when you marginalize out some variables. Like in this case, if we're only interested in the probability of x1, then I will sum these whole probabilities over the different values that x2 to xn can take. Okay, and then I will end up with just x1. Conditional probability distribution, abbreviated as CPD, this is P of, for example, here x1 given x2 to xn. You can of course end up with like x1 and x2 given the other variables or whatever. This will be all of the variables here, the probability, the joint probability divided by the condition part by definition. And then how we calculate this is by itself a marginal distribution. Okay, so I need to take the whole distribution, the joint distribution of x1 to xn, and then marginalize out x1. I will end up with the denominator, and I can put it here. Another recall is on the number of parameters of a distribution. Given discrete random variables x1 to xn, just imagine that x1 takes alpha 1 values, x2 takes alpha 2, and xn takes alpha n. Then the number of parameters to represent the joint distribution is just the multiplication of the different values they can take. Like in the previous example here, we had 2 times 2 times 2 for C and M and D, and then -1. And the same holds here. In general, we have alpha 1 to alpha n, just -1 because they add up to 1. If we're interested in a conditional distribution, then the same story, x2 to xn take these many values, okay? But x1, we know that for each of these instances of x2 to xn, it takes alpha 1 different values, yes, but they add up to 1. So that's why we multiply it by alpha 1 minus 1. And a little example here, our COVID mask social distancing example. I'm using this notation, which is often used in the literature instead of true, false, or 0, 1. Sometimes a variable m or x or whatever, a superscript is used with a number indicating the which value of this variable we're interested in here. So here, for example, m is the variable, and m1 means that the first value of this variable. d2 means the second value of this variable d. So here m1 is basically false or 0, and m2 is true or 1. Or it can be the other way around. This becomes more important when we go to here, where we cannot like just simply say 0 or 1. We don't know what many values they can take, so we use this notation. So anyways, we can have 4 different possibilities for m and d, and then the variable of interest c can also take 2 values, and for each instance of m and d, like here, then I should determine the probability of C1, like the first value that C takes. For example, here it's 0.5, and then automatically the other one will be 1 minus that, because they should add up to 1. Okay? And so on. So for example, if M1 and D2, then this probability can be 0. Here it's 1, and they always add up to 1. So you can see that it's 4 times 1 here. So I need 4 different parameters. If I just indicate these 4, if I determine these 4, then these other 4 will be obtained automatically. And in the general form, I can have x2 to xn. This is the probability I'm talking about. So for the last variable, so x2 to xn minus 1 are all fixed in this part. Only xn is changing from 1 to alpha n, so I will have alpha n different possibilities, and then I will repeat it for xn minus 1 to x2, so I will end up with this like block being repeated many times. I mean, as many as like alpha 2 times alpha n minus 1. So I will have these many instances, and for each of them I need to have the values of x1, which in this case are 1, 2, 3 to alpha 1. Just that again, this one of them, for example, alpha 1, the x1, the superscript alpha 1, will be the will be obtained by 1 minus the remaining of the values. So I just need to calculate or to indicate these ones, and that's why this alpha 1 minus 1 appears. Okay, so just these two numbers formulas can help. Okay, to summarize, what is the goal of this whole chapter, and maybe even the whole this whole course on Bayesian nets? The goal here is, given a data set, how can we obtain the joint probability distribution of those variables of interest? Okay, and we already saw why it is important to know this joint probability distribution, because we can answer any probabilistic inquiry if we know this. And you may say, well, okay, why should I take a whole full course to answer this? Well, one reason is this: let's get one step closer to the real world. More variables. In reality, it rarely happens that your task is as simple as just 3 variables. You are given many variables sometimes. Well, in this case, they're not many. They're just 12 variables. So COVID, mask, social distancing, we already had. But now imagine that we also have collected data on the individuals, whether they had flu or cough or fever, whether they had a proper ventilation system, what was the season. This one, unlike all the other ones, take 4 values. Congestion, difficulty breathing, whether they use drug or not, and allergy. Okay, how many individuals? Well, if you have a really good data set, it will be 1,000. In most of the cases, it's much less. Okay, so number of required parameters, if we want to use the previous approach, 2 to the power of 11, because there are 12, 11 of them are binary, times 4, because season is 4, minus 1, because they add up to 1, which is around 8,000. 8,000 parameters. How many instances we have? Only 1,000. So what should we do? So ideally, if even we can estimate each parameter by just a single instance, I don't know how, but like imagine you can do that. So you will end up with 7,000 parameters that are not estimated. And what should we do? We should just set them to 0? No, because the fact that an instance does not appear in our data does not mean that it will never or even rarely happen. So what we did here, that we just set it to 0, for example, this was almost a naive approach that we took here, especially the error of taking this approach will reveal itself when we take these many variables. So you can imagine if we set all these 7,000 variables to 0, what can happen? We probably will not have a good model here, that we cannot answer inquiries properly. This is already a challenge, right? And what is the solution? If you want to know the answer, watch the next video, and thanks for your attention.